In system design discussions, engineers frequently use the terms scalability and high availability interchangeably. But managing high incoming traffic and surviving a sudden catastrophic disaster require two completely different physical system architectures. We will start with scalability. This is a system's inherent ability to dynamically adapt to an influx of processing load and traffic spikes. Vertical scaling is the first adaptation. If a node is overwhelmed, replace it with a powerful machine containing more CPU and memory. Alternatively, horizontal scaling distributes the workload. Instead of upgrading, you add identical parallel nodes to process simultaneous data streams. But consider the physical reality of that parallel grid. If the data center housing those nodes loses utility power or catches fire, the entire fleet goes offline instantly, completely and immediately halting all business operations. Surviving localized physical disasters without service interruption is the exact definition of high availability. To achieve it, you duplicate your entire infrastructure into a completely separate geographic facility, ensuring the destruction of one building does not take down the system. A robust system architecture demands both, layering elastic load management on top of geographically isolated fault boundaries. Let's translate this conceptual model into the exact physical realities of Amazon EC2 instance families. This chart displays the spectrum of AWS compute capacity. At the absolute minimum baseline, designed for minor, bursting workloads, is the T2.Nano instance. It provides just a single virtual CPU and 0.5 GB of RAM. Scaling this vertically means stopping the instance to alter the raw hardware allocation assigned to the guest operating system. That process introduces a critical engineering limitation. It mandates a system reboot. During the transition to a larger size, like an M5.2XL large, the instance incurs unavoidable downtime. If you continue to size up, you will eventually reach the physical extreme of the hypervisor hardware, hitting a hard architectural wall. This barrier is the U12TB1.𝗏 instance. It is an enormous machine, delivering 448 virtual CPUs and 12.3 terabytes of RAM. Legacy monolithic relational databases rely almost entirely on this vertical scaling method to handle growth, meaning they will inevitably hit this unpassable physical limit. Since individual physical servers possess a strict maximum size, adding smaller instances in parallel through horizontal elasticity is the only viable path for infinite workload expansion. With the compute capacity limit established, we have to address the threat of physical infrastructure catastrophes. This map outlines a large-scale geographic operating boundary. In AWS, this is known as a region, in this case, the Asia-Pacific Sydney region, designated as AP Southeast 2. By design, every AWS region operates under a strict structural rule. It must contain a minimum of 3 and a maximum of 6 availability zones. Within the Sydney region boundary, you can see 3 distinct, widely spaced clusters, sequentially labeled A, B, and C. Each of these clusters operates with independent internal hardware redundancy. They have their own dedicated backup generators, cooling infrastructures, and utility power feeds. The physical distance separating these clusters is deliberately engineered to ensure that localized floods, fires, or power grid failures cannot impact more than one zone simultaneously. To allow these distant facilities to act as a unified distributed system, they are interconnected in a ring topology by high-bandwidth, ultra-low latency private fiber-optic networking. This ultra-low latency fiber fabric is the absolute prerequisite for synchronizing data across zones and making active multi-AZ failovers physically possible. Once this multi-AZ physical topology is established, systems architects face a mandatory choice between an active or a passive execution model. This flowchart compares the two models. In an active-active high-availability setup, a load balancer dynamically splits incoming traffic, allowing provisioned compute instances in both availability zones to receive and process data simultaneously. Distributing active work across multiple zones like this is the required standard design pattern for horizontally scaled, stateless web applications. The opposing model is passive or active-passive high availability. Here, a secondary resource is fully provisioned in a separate zone, but it remains idle. It refuses live client traffic under normal conditions, sending 100% of the workload to the primary node. Amazon RDS multi-AZ deployments are the definitive example of this passive execution model. The primary database handles all reads and writes, while the underlying block-level changes are synchronously replicated across the fiber network to the standby database. If the primary availability zone suffers a physical disaster, AWS automatically detects the outage and redirects the connection string, instantly promoting the standby database to take over the active role. Passive high availability simplifies stateful data preservation, but it comes at the heavy financial cost of paying for idle reserved resources. Active high availability avoids this waste by maximizing compute utilization across the entire fleet. We can now merge these standalone concepts into a holistic, multi-tier architecture. Incoming traffic hits an active-active web tier, scaled horizontally across 2 zones, which then writes state down to an active-passive RDS database tier below. The strict architectural rule applies at every layer. Scalability manages the fluctuating compute loads, and high availability ensures survival against data center destruction. The web tier requires horizontal elasticity, because, as we saw, vertical scaling terminates entirely at the impenetrable 12 terabyte memory ceiling of bare metal hardware. Expanding a fleet horizontally across multiple geographically separated availability zones creates a massive network routing challenge. How exactly does an architecture actively monitor node health and safely distribute incoming client requests across such a highly parallel multi-zone environment? This orchestration of stateful session routing and multi-AZ network paths is the exclusive domain of elastic load balancing, which we will analyze in the next part of this series.